Okay, so last time I told you we were going to do coplanar and 2D problems today. Having then pieced this together, the third part that I said we were going to do on graphs, we're not actually going to be doing today because I figured it was too much to actually get through in one session. Okay, so we're just going to do the coplanar and the 2D problems. Okay, so starting with a quick recap of what we've done, because you need to know these inside out for electrostatic and for gravity. We've got Coulomb's law, 1 over 4 pi epsilon 0, Q1, Q2 over R squared. You need to know the electric field strength, so its definition, the force per unit charge. And then expanding that, we get 1 over 4 pi epsilon Q over R squared. We also have the electric field strength is the voltage over the distance when we're looking at a uniform field. Then Coulomb's constant, so we can call it K, that's 1 over 4 pi epsilon 0. Okay, which, as we've talked about, is approximately 9 times 10 to the 9. But obviously you use the figure given in the data booklet or the question. And then last two, the electrostatic potential, so VE. Something we look at is that it's delta of the field strength over the change in distance. And that gives us 1 over 4 pi epsilon 0 Q over R. And the last one then, so the work done exactly the same as for gravity, is the change in potential multiplied by the thing that's being moved. So multiplied by the charge, but that charge is specifically the one that's being moved in the field, not the one that's creating the field. Okay, so that's a quick recap for you. So we're going to start with coplanar problems, and so there's two types you can look at for this. Each of them can be looking at either the force that's created, the potential, or the field strength. Okay, and I'll be saying this several times, that whenever you're doing the force or the field strength, okay, you need to remember that they are vectors. And the potential is a scalar. Not so important during the coplanar ones, but very important during the two-dimensional problems. So you can either have them where you're calculating the overall value in a setup, or you can have it where you're finding a specific point where the forces or the field strength cancel each other out. So you're aiming for a point where those values would be 0. And they're not always necessarily at the same point for the force, the field strength, and the potential. Okay, so you do have to work them out individually if required. So the first one then, as an example, this will be in the booklet that you'll have a copy of once we finish the topic. Okay, so with this, you've got a simple setup, two charges, one negative, one positive, and we're looking at the resultant field strength due to those charges at point X. Okay, so pitfalls for this is not noticing that this one's negative and this one's positive. Okay, and then for B, using a distance of 5 millimeters, because that's just the nearest value. Okay, so A should be simple enough. It's minus 2 nanocoulombs at 5 millimeters, but then B is plus 2 nanocoulombs at 10 millimeters. So the first thing you'd have to do is find the field strength for A. Okay, now I've included the minus, but I would point out that that is only to verify the direction. Okay, so the plus or the negative nature of your final answer only tells you which direction that's acting in, and obviously you have to assign that direction appropriately. So for X, we would be assuming that we placed a positive charge there. So when we get that negative value from A, it would be attractive. So it's acting to the right. And then any positive values would be acting to the left. But when we give our final answer, we should not have a negative sign in it. So that electric field strength, you can't have and a negative electric field strength, the minus only signifies the direction. Okay, so do bear that in mind when you're answering questions, to take away a negative sign. But obviously, when you're combining them, combining A and B, you do have to pay attention to which one's negative or positive to make sure you combine them correctly. Okay, so we get a value of 720,000 roughly for that one. We do exactly the same for B. Now, because B is positive, we end up with a naturally positive answer. We do have to pay attention to that. So that one now means that it's going to the left. So when we combine these two, they're acting against each other. So rather than doing the sum of it, we have to work out the difference. Okay, so the final part is combining them for the resultant. So we've got negative 719,000, positive 179,000. So the difference will be 539,000 to the right because the negative is bigger. But the final expression shouldn't have that minus at the front. Okay, so you can leave them in there when you're doing your calculations to make sure you don't make those mistakes, but make sure you don't leave that negative in there at the very end of your answer. Okay, but you should include a direction for it. Okay, so just to recap, you do field strength for the first one, for A, field strength for B, and then combine them appropriately depending on whether they're both the same charge or different charges. Okay, so there's one for you to try. I'm going to give you 5 minutes and then we'll run through the answer. Okay, so we've had about 5 minutes on that, so we've got you run through it then. So you should have found the electric field due to A, 1 over 4 pi epsilon 0 Q over R squared. So I'm using 9 times 10 to the 9 for Coulomb's constant, so 1 over 4 pi epsilon 0, multiplied by minus 6 times 10 to the 9. So I got my minuses in the wrong place. So it's 9 times 10 to the plus 9, multiplied by minus 6 times 10 to the minus 9, divided by 2 times 10 to the minus 3 squared. When you plug that in, you should get an answer of minus 13.5 million. That is in newtons per coulomb. When you do the same for B, you get a final answer of plus 17,280,000. Okay, so that first one will be acting to the right because it's attractive, and we assume we put a positive charge at X. So this one will be acting to the left because it's repulsive, and therefore the one going to the left is winning, so that will be our final answer. So our resultant is a combination of those two, which is positive 3,780,000. Okay, and because it's B that creates that bigger electric field strength, that will be acting to the left. It's repelling the theoretical positive charge that we have placed at X. Okay, so hopefully that's fine, and there's more for you to try in the task that I've posted in the assignment. Okay, so that one. Okay, so yeah, you've got to be really careful with those squares that they don't disappear. Happy to move on? Okay. Okay, so then your second type for this is where you're calculating where two things effectively cancel each other out. So you're looking for a point where they become zero. Now these are more common because it's not just about picking an equation, it's about using your common sense. Okay, so we've got a situation here where we've got 18 nanocoulombs, 2 nanocoulombs, and a distance of 12 centimeters. Okay, so the process you go through for this is you write out the equations for each point charge, and you know for them to be at zero, those two things must be cancelling out, so they must be equal and opposite. Okay, so you can make those two equations equal to each other. Then you get rid of the like terms in the equation, and then you have to look at the ratio of the terms. You're going to end up with one fraction equal to another fraction. So you have to consider the ratio of the top values and then replicate that ratio in the bottom values. Okay, so we've got an example to go through for that, and it's important that you can do this. Okay, so we're looking for field strength, so we're looking for E, and we're looking for a point where the field strength of A cancels out the field strength of B. So we're looking for a point where EA is equal to EB. So if we write out the two equations for it, we have EA equals 1 over 4 pi epsilon Q of A over RA squared. And that must be equal to E of B, which is also 1 over 4 pi epsilon, but this time it's QB over RB squared. Okay, so we're essentially just going to take out the EA and the EB and make those complex sides of the equation equal to each other. Okay, so that becomes equal to that. At this point, we can cancel like terms. So the constant at the front disappears. And we're left with QA over RA squared is equal to QB over RB squared. And this is a situation where it's essentially just creating two identical fractions. So if I said to you that we had 1 over 2 is equal to 7 over x, I'm sure you could all figure out that x is going to be 14. Okay, the top numbers, one is 7 times the other one. So the bottom numbers have to follow the same ratio for that to work. And that's exactly what we need to do in these situations. You could come up with an equation where if you label that as the point that's going to be 0, and that would be RA and that RB, you could say that RA plus RB equals 12 centimeters, and then use that to substitute in to form a quadratic. But it becomes very complex if you go down that route, and it's difficult to solve. That's part of the reason why you have here that bracket S, because if you do the quadratic, it should come up with 2 solutions. Okay, but in reality, there is only one. Okay, so you need to do the ratio to do this quickly. Okay, just get rid of that. Okay, so we substitute our values in. So for QA, we have 18. So it's going to be 18 over RA squared is equal to B, which is 2, over RB squared. Okay, it's going to change my pen. Okay, so you have to look for those ratios then. So those top numbers, if you look at those, okay, this one is 9 times as much. Okay, so 18 is 9 times 2. And therefore, RA squared must be equal to RB squared times 9, because it's got to follow that same ratio. But then we can add in square roots. So RA will be equal to RB times the square root of 9. So times by 3. And it's that ratio that's important, that RA is 3 times bigger than RB. So we've got 12 centimeters to play with. Every centimeter that goes into RB, 3 centimeters need to go into RA until we reach 12. So we end up with an answer of RA will be equal to 9 and RB will be equal to 3 centimeters. Okay, now you can express both of those as long as you label your diagram correctly, or the question might specify how far away from B is this point, in which case obviously they want the 3 centimeters as your final answer. So you have to read the question carefully. But the only way to do this quickly is by looking at those ratios. And I will say, of all the questions I've seen in exams, they tend to pick ratios of the charges that happen to be a square number. So it's either going to be 4 times bigger, 9 times bigger, 16 times bigger. Okay, because that when you square root it, then it makes it far easier to come up with decent numbers. Okay, on the odd occasion that they don't have a square number, the decimal that's produced by the square root then still generates a nice answer at the end for RA and RB. Okay, so you shouldn't end up with, for example, RA being 1.792648 centimeters. Okay, you've probably done something wrong along the way if you come up with something like that. Okay, obviously that might not be true in the questions I've written, okay, because obviously I just pick numbers out of thin air and go with it. But for an exam, you should be ending up with a nice number at the end. So there's one for you to try. I'm going to give you 5 minutes on this as well to have a little look and see how you get on, and then we'll run through it. Okay, so I had 5 minutes on that, so let's quickly run through. I won't go through all the writing the equations out and cancelling like terms. Should be able to do that or refer back to the previous slide. I am, however, going to go back to a red pen. Okay, so once you cancel those like terms, you should end up with QA over RA squared equals QB over RB squared. And then you substitute your numbers in. So we've got 40 over RA squared equals minus 10 over RB squared. Now we're going to ignore the minus for now, but the key point is that the top numbers have a ratio of 4 to 1. Okay, so if QA is 4 times bigger than QB, then RA squared must be 4 times bigger than RB squared. So RA squared equals 4 times RB squared. And then when we square root, we end up with RA equals 2 times RB. Now, at this point, there are two possible solutions, and it all depends on whether you've paid attention to the minus or not. Okay, so if you hadn't, you would get an answer where you just drop 1 mark. When you look at that ratio, you've got 4 centimeters to share, and one needs to be double the other. So you might have ended up with an answer of RA equals 2 2/3 centimeters, and RB is 1 1/3 centimeters. And that fits our ratio. However, that places the point somewhere in the gap, and they won't be cancelling out at that point because they're acting in different directions because of that negative. So in fact, the point where they cancel out has to be beyond B. It has to be this side of B, because we're imagining we're placing a positive charge. So B is going to be pulling it that way, and A is going to be pushing it further away. So we need those to cancel out. If that positive charge is placed inside, then it's going to be attracted to B and move that way, and A is going to repel it and move it that way, and therefore there's not a 0 resultant field strength. Okay, so the actual answer you should have ended up with for full marks would have been that RA is 8 centimeters and RB is 4 centimeters. Okay, so it's actually 4 centimeters beyond B, giving a total of 8 centimeters for A. Okay, so if you did the 2 2/3, you'd have got all but 1 mark, and if you ended up with 8 and 4, you'd have got full marks on that question. But you do need to pay attention to the charges as well to know whether the 0 point is going to be between them or one side or the other. Okay, some people also might have said, well, okay, I'll go this side of A instead, because A will be repelling it and B will be attracting it. But because A is a larger charge, it's going to have to be a very well thought out situation. In fact, I don't think it's possible for that to happen. Okay, A is always going to create a larger field strength than B if it's closer. So it can't be that side of A. Okay, so you just have to think a little bit about where that point's going to be when you do these. Okay, I will tidy that slide up before I post it for you. So moving on to 2-dimensional problems then. So we did these for gravity as well, so you should be familiar with them already. Okay, it's where you look at one charge, and then for the force and the field strength, you would have to do a bit of trigonometry to make them horizontal and vertical. Do the same for the second charge and combine those horizontal and vertical values to get a final vector, a final value with a direction. And as I mentioned in gravity, if you just take a moment to look at the situation and see where they've simplified it for you, because they don't want to be awarded marks for doing trigonometry twice. You either can do it or you can't. Okay, so the example I've gone for here, it's all the same sides on the triangle and same charges. So whatever one does, the other will do the same as well. So you've really only got to do one and then effectively double it or cancel out for B. Okay, so there's one to run through here. Okay, so the first point on this is that A and B are the same, and therefore EA will be very similar to EB. Slightly different direction, okay, but we'll deal with that when we get there. But in terms of values, we can effectively either cancel them out or W. So we're going to double them. We're going to focus on A, start with an A's influence on point X. So EA is 1 over 4 pi epsilon times Q over R squared. So we end up with 9 times 10 to the plus 9 multiplied by 4 times 10 to the minus 9 divided by 8 times 10 to the minus 2, and that is squared on the bottom. Okay, so don't forget to include that squared. And we end up with a final answer of 5625. Okay, now that, because we're imagining we're placing a positive charge at X, that is acting away from A on that line AX. So it's acting in that direction. 5625. Now B will do exactly the same, but along the line BX. But those two things can't be easily resolved as they are. So the first thing you're going to do is resolve this 5625 into horizontal and vertical components. Okay, but the savvy students amongst you will notice that because B has the same charge, B will produce an identical force, sorry, not force, identical vector along that line. So we don't really need to worry about the horizontal components because they will eventually just cancel out. So in fact, they're going to completely ignore those. Other students amongst you that are switched on and looking at the sides will realize that this triangle, because it's got equal sides, will have equal angles. So this angle will be 60 degrees. And therefore this angle will be 30 degrees. Okay, because it's that angle cut in half. Okay, so we're turning through the angle. So this will be 5625 cos of the angle, so cos 30, which gives an answer of 4871.4. But that is just from A. B will do exactly the same. So as I mentioned, the horizontal ones will be in opposite directions, so they will cancel each other out. But the vertical vector will be in the same direction. So we then need to double that. So times 2 for B. And we end up with a final answer that E resultant equals 9742. And adding our direction, it would be downwards. Okay, or if you were given bearings or compass points or whatever, you would say south. Okay, as long as you include a relevant direction. Okay, so pay attention to the setup because they're going to give you something that simplifies the process. Okay, there'll be extra stages at the end, as in, thinking about whether they cancel or combine those forces. But it's unlikely that they're going to give you a weird shaped triangle that's going to take forever to do, because then they're going to have to award you like 12, 13, 14 marks for it. Okay, so there's one for you to try now. Again, I'll give you a little longer on this one, and then we'll run through it. Okay, so I had about 8 minutes on that, so let's run through it. Okay, so perhaps doing things in reverse order on this, looking at the logical aspects of it, the sort of things you can consider straight away before you get into the actual question. Okay, so first of all, you should notice that they're all 10 centimeter sides on the triangle, and therefore, because they're all equal sides, all the angles will be 60 degrees. The second thing for this, you should notice that the two charges at the top and the bottom points are positive, whereas the one at P that we're actually, the point we're interested in, is negative. And think about how that's going to influence the direction of the forces. So if we look at B first of all, because they're opposite charges, that's going to be an attractive force. We're going to have a force acting along that line. But actually we're going to resolve that into a horizontal force, which I'm going to call FBH. Sorry, should be vertical, shouldn't it? FBV. And a horizontal force towards O, which would be FBH. Then considering A, both opposite charge again, so we're going to have that attractive force, so it's going to have a downwards force, FAV, and another horizontal force, FAH. Now, because they're both the same charge, you should realize that FAV will be equal and opposite to FBV. So therefore, those two forces cancel out and we're not really interested in them. You should also realize that these two are going to be an equal size. So once we've worked out one, we can just double it. Okay, so it's the same process again. Okay, so if you take that time at the beginning to have a little think about what's going on and then actually work your way through it. Okay, so I'm going to focus on, well, it doesn't matter which one you focus on really, but I'm going to focus on B because it's at the top. No, I'm not going to focus on A because I'm in that colour pen. So I end up with 1 over 4 pi. So I think the battery on the pen's dying, which is why it keeps jumping. 1 over 4 pi epsilon Q1 Q2 over R squared. Okay, remember to square it, and remember we're working in centimeters as well. And when you plug that in, you should end up with a force of 5.4 times 10 to the minus 6. Okay, that's the force acting along the dotted line AP. 5.4 times 10 to the minus 6. At that point then you need to do your trigonometry. Okay, so we know that this angle at P, the full angle is 60 degrees. So therefore OP splits it in half, so it's going to be 30 degrees. So the horizontal component of the force due to A is going to be 5.4. Oh, that's very messy. 5.4 times 10 to the minus 6. We're turning through the angle, so it's cosine of 30, which gives us an answer of 4.7 times 10 to the minus 6. It is a lot longer than that, more decimal places. But then because FBH will be the same size, acting in the same direction, we then need to multiply that. Okay, so the F total, or F resultant, will be 2 times FAH. And we end up with a final answer of 9.4, or came out at 9.35 times 10 to the minus 6 newtons. Okay, so you have to be able to do that trigonometry, just like you had to for the gravity section of the topic. But as I mentioned earlier, when we're doing this, if you're doing force Force is a vector, and therefore you have to do the trigonometry. The field strength is a vector, so you also have to do the trigonometry, but the potential is a scalar. And therefore, when you do if you were working out the total potential at point P, you just work out the actual values, and it doesn't matter about direction at all. So you just add them or take them apart depending on the charges and the signs and the setup you've got. Just literally just work out the two values and combine them correctly for potential, because it doesn't have any direction. Okay, so